Hi there, and welcome to a review of stress-strain curves. What we have here is the stress-strain curve of a mild steel bar that has been pulled in tension, like that image in the bottom right corner shows, and we are plotting the force versus area on the vertical column, and our horizontal is, of course, the strain, which is the change in length over the original length. And so we have our stress versus strain curve for our mild steel. And we picked mild steel because mild steel is easy to see when it yields, because you get that lovely little plastic region right at sigma yield. And of course we have our peak stress, which is our ultimate stress. Now that line should have been a little more linear between where you have the yield, stress, and strain, so go ahead and clean that up. And if you recall, our sigma yield is the stress. It's an important stress because it is the stress that occurs right where the material yields, which means after this loading, if you continue loading after this point, you're going to have permanent deformation. You internally yield the atomic structure, the crystal planes, and you will have permanent deformation in the material if you load it after this point. You can, under this value, load and unload, load and unload, like pulling and releasing a rubber band, and not see any permanent deformation. Now, if we load past sigma yield, we continue loading until we get to the maximum load that we say our material can take, and based on engineering stress, we would call that our sigma ultimate. And the sigma ultimate is still found using P over A, and that's the original cross-sectional area. And so when we do base this ultimate load, it is on that, it's called the engineering stress, because it is based on the original area. And what we like to do in design is we very much like to keep our loads under the yield stress during regular loading, and if at all possible, well below the yield stress, and you don't go above yield unless you're talking about a major event. Say if it's in buildings, if an earthquake's going to hit, you can go beyond yield but stay below ultimate. If you're designing, say, a vehicle in day-to-day loading, driving, people in the car, you would have the loads below yield, but during a car crash, you might accept that the loads would go above ultimate, or to ultimate, hopefully not above. All right, now after yield, you get this long range that we call our plastic range, and you would also have then the areas of strain hardening and necking that we can see up there on the curve. And so after a material has yielded, especially when you're talking about a metal, the atoms are all aligned in a crystal structure, and they can slip, and that's our plastic behavior. But there's usually going to be flaws, whether they're intrusions or inclusions of other materials, whether they're a grain boundary or whatever's happening when that metal hardened. The slip planes will hit one of those flaws, and then it takes more load to get the material to continue deforming. And so you get this area of strain hardening because it's sliding along, we got a nice little plastic slip, and then bam, it hits a grain boundary and the material can no longer slip. So you have to push harder to get it to continue deforming. But at some point, we start necking, we start losing cross-sectional area, and so the load that the material can take starts dropping, and then we get our area called necking. And as part of this assignment, you're also to watch a video that you've been linked to that just shows a stress-strain curve. So watch that and you'll be able to see the necking happening visually and see what's going on. Now, another really important thing that you can get off of the stress-strain curve is whether or not a material is a ductile material or a brittle material. And this is really important, and I hope you do not leave this course without knowing what is ductile versus brittle. So ductile materials can experience a lot of deformation after they yield, but before they actually break, versus a brittle material which will fracture almost immediately after it has yielded. There are a lot of applications where a ductile material is really preferred. I'm a structural engineer, and so when I'm designing buildings, I don't want a brittle material that as soon as the material yields, it just fails and falls down and collapses on people. I'd rather have it have a long period of deformation where you can actually see it deforming, but it can still carry load. So you have what I would call runtime, people can get out. If you're designing the machinery or any sort of support for something, then you would want the same thing, because you don't want things to catastrophically immediately collapse without warning. And so remember, though, the key thing about how we judge if something is brittle or ductile is all about the deformation that occurs after yield. Before yield, that deformation gives us a measure of E. Remember the modulus of elasticity, your good buddy Young's modulus. Young was smart enough to notice that if you just looked at the ratio in the linear section, it was constant in the linear section. Big ooh-ah. But notice that you could take stress over strain, and not necessarily the yield stress, but the stress over strain, and if you load and unload the specimen back and forth in the elastic range before you've yielded, that the curve just loads and unloads and loads and unloads along the same path. And again, imagine a rubber band. You pull it, you release it, you pull it, you release it, you end up with zero deformation when you have zero load. You're just back and forth on the same line. But if you load it too much and you load beyond yield, then when you unload, you would actually unload and you don't come back to zero. And instead of coming back to zero deformation, you end up with this permanent deformation or permanent strain if you're on the stress strain curve. And when you reload from the point where you unloaded with that permanent deformation. And so you can actually see you go higher up the stress strain curve along the elastic slope upon reloading. All right, but you're always loading and unloading along that Young's modulus curve, that stiffness curve. And so Young's modulus is so important. Let's sort of look at a couple different materials. So we're going to look at some curves for different materials on stress strain curves. We'll start with a concrete, an aluminum, our mild steel again there in black, and then a high strength steel that goes up it's the same slope as the mild steel. So again, concrete is the purple, mild steel is the black, aluminum is the green, and then a high strength steel. And if you notice, the initial slope of the mild steel and the high strength steel are basically the same, and steel has a Young's modulus or a stiffness of approximately 30 times 10 to the 6 psi, where aluminum is around 10 to the 6, 9.8 up to 10.4, different experiments show depending on the type of steel. Concrete's modulus of elasticity is a function of the concrete strength. So if you happen to have designed a concrete that has a strength of 4,000 psi in compression, then you end up with a Young's modulus of about 3.6 times 10 to the 6 psi. Now, Young's modulus is really a measure of the stiffness of the material. We say how stiff is something. And so which do you think is a stiffer material? The steel or the concrete? Now, you could just say, well, the steel has the higher number, so therefore it must be stiffer, but that doesn't really help you understand what on earth stiffness means, right? Because that's what you really want to understand. So stiffness is a measure of how much force does it take to get something moving. If it's really flexible, it's not stiff, right? So you know when you have a high E, that's telling you that you've got to push harder on that material to see any deformation. It's not a flexible material, it's a stiff material. So steel is obviously the stiffest material on this plot, and concrete is the least stiff. You don't think of concrete as very flexible, but remember, I didn't say they're flexible materials. It's all relative to stiffness. We can't push any of them, but if you had a machine, it might be a different story. Now, since we were talking about earlier how important ductility and understanding what a ductile versus brittle material is, look at that plot And what is the most ductile material on that plot? Is it the aluminum? Because the aluminum just slightly has more strain than the mild steel, so the aluminum definitely fractures at the largest strain value. But is it the mild steel? Because the mild steel yields much earlier than the aluminum. And in fact, if you look at the aluminum, you can see that it doesn't really yield on this particular plot until well after, or until about, till about, well after the mild steel, but about where the aluminum line crosses the mild steel. So you have a really much shorter range between yield and fracture for the aluminum than you do for the mild steel. Aluminum is a less ductile material than steel. It is ductile, but on this particular plot, the mild steel is the most ductile material. Now you might also have noticed that the high strength steel, aluminum, and the concrete don't have that obvious yield point like the mild steel. And so you're going to have to go back to that 0.2% offset rule that you should have used in the past already to find your yield stress, but we will use that in the lab. Your book does a great job explaining it, and we'll do a little review of it during the lab on how to use the 0.2% offset to find yield for materials that don't have an obvious yield point. And there's one more bit of material that we want to get off this curve. Whoops, we're going to go back. And what that is the true stress that we have there marked in the red cloud. So remember we said necking occurs, and when necking occurs you actually get a reduced cross-sectional area. Your load also drops, but your area is reducing by more than the load is reducing. So when you find your stress P over A, you actually would get a higher value than what you get by using the reduced P with the constant cross-sectional area. And so that's really the true stress. We don't use that. We use engineering stress because, one, it's much easier to calculate than trying to figure out what the area is at any instantaneous moment. But also, it's more conservative because then we say sigma ultimate, bam, that's the max stress it can take before it breaks. And if we slightly load it over that, it's possible that we can still hold load before it fails. And so it's just a measure of safety. All right. So there's one more thing that we do want to see off of our stress strain curve, and that's going to be something called our strain energy. And so the strain energy is really nothing more than the area under the stress strain curve. And there's two different parts of the curve that we can look at when we're looking at the area under the curve. We can look under just the linear region. And this particular plot doesn't have an obvious yield point, so we'll go to the end of where it's proportional, the stress and strain. We'll call that the proportional limit, PL. And here we can look at the area, which I've just dashed in red, and that area, which is just a triangle, would be the modulus of resilience. And so the modulus of resilience is a measure of how much energy it can take before it yields, how much energy you can get back out. So say you're doing a torsion bar and you want to let it deform a little bit and snap back and deform and snap back. You can think about the energy in a rubber band before you release it, right? That's your modulus of resilience. How resilient is the material to yielding, and what will you get back to it? Again, simple area formula, 1/2 sigma PL, right, times strain PL at the proportional limit when it stops being proportional. But we also have the area under the entire curve, which we can mark there in green lines, and that's going to be your modulus of toughness. And that tells you how much energy can the material absorb before it fractures, before it absolutely fails. And the modulus of toughness is really important, say, if you're designing crumple zones in a car, for people who study fracture mechanics, and that's just another bit of information that you can get off of the stress strain curve. So I hope you enjoyed this review. Don't forget to watch the video of a real stress strain curve. Hopefully you watched that beforehand, or a real stress strain test. Thanks a lot.